Good morning, everyone. We've got people still trickling in, so we'll get going here in about 5 minutes or so. Just another minute or two, and we'll get going. Okay, we can go ahead and get going and see if anybody else joins us this morning. I want to thank everybody for joining this morning for this webinar. This is our second webinar of a three-part series. So anybody that's joined the first webinar, machine guarding for risk reduction measures, thank you for joining the second one. If that's something that you missed, we do have more scheduled in January that I can send out links that you can join for. Those have not been part of the webinar series. I'll introduce myself. My name is Sean Mantell with PowerSafe Automation. We're a turnkey machine safety solutions provider. We do everything from the guarding assessments and custom design of the guarding, manufacturing, assembly, and installation and electrical integration. We do that nationwide. So it basically starts with coming on site after a initial teams meeting to get an overview, and then collaborate with your operators, maintenance, safety, just to get a scope of work concept, set some goals and targets. So that's who we are. You can learn more about us at our website, which I'll show here in a little bit. And then this one's going to be based on control reliability for functional safety. I have two people on with me that is going to help with the chats. Basically, what we're going to do is we're going to go through the presentation. If you have any questions, you can drop them in the chat. One of them can help with if you need to schedule any additional time with PowerSafe Automation after this. And then that'll be Tracy. And then Marcus Vernon is TUV certified safety engineer that helps out with the risk assessments when on site, whether it's just for machine guarding or get into some of the control work. So if there's no initial questions, I'm going to go ahead and turn my camera off and share my screen so we can get started on the presentation. Everybody see my screen okay? Okay, we'll go ahead and get started. So this training today is going to be achieving control reliability through functional safety. It is what we look at with safety is two parts. One from the machine guarding standpoint for hazards that humans can make the decision whether they are going to bypass any devices, open gates when they're not supposed to, really giving the human the thought process of what am I going to do to make sure that I'm safe or unsafe. So the machine guarding is what we put in to take that essentially away from operator thought process. And then the functional safety portion of it is making sure that the brains of the machine take over for the human thought process to make sure that that's reliable and making good decisions, making the right decisions, effective decisions, consistent decisions. So that's what today's training is going to be about. So everybody is I'm assuming understands or has heard OSHA, ANSI, NFPA, NEC. These are basically the codes, regulations, standards that are used to either police your systems or to help you build your systems and stay compliant, risk reduction, all of that that is wrapped around that with both the machine guarding, all the electrical standards that go into all the wiring and what your control panel should look like when you are looking to have a compliant machine or a machine that you're reducing the risk for your environment. There is no grandfather clause to not guard your equipment, upgrade your controls. I understand that there are a lot more costs associated with the control portion of it versus putting up guarding with the right devices. But it is still something that is required out there for you to make sure that you are protecting your employees the best that you can. And the goal is to mitigate hazards by stopping machines, slow speeds to a safer foot per minute, and moving hazards to a safe position. So really what we need to start with is defining what stored energy is. Stored energy is trapped in a machine component that can release suddenly and unexpectedly. We need to make sure that we are managing that stored energy properly. Are we bleeding it off? Are we trapping it? Are we holding it tight? What is the operation we need to do? Does it need to stay under load? And if the answer is yes, then how do we make sure that that load is held safely? Do we need to exhaust it off so that if we need to move parts around, climb into a machine, whatever that is safely released so that we can work safely around a machine that doesn't have any of that stored energy? You'll see these signs. If you see signs like this, these signs should automatically have you ask the question, why is there a sign up here? If there's a sign somewhere, that means that there is a danger, a hazard, something is there. If there wasn't, those signs may or may not exist. So, but if you do see a sign, ask the question, why are these here? And if they're there, now you can start the analysis of, okay, this is here because of this, and it has the potential to do that. So just a quick visual for you to see what is going on in your area and how to identify those. And then why is it important to control stored energy? Uncontrolled stored energy can release, can create jams or clear jams. There was a situation a couple years ago where a slide hammer was sliding back and forth, stopped, bound up in the middle. The e-stop was pressed. The controls, the programming didn't say to bleed off the pneumatics, which was powering that slide. It only disabled the energy for the electrical. And what had happened is the person went down to look at the bearing track as to why that bound up. The air was still stored up and it was building pressure, and it kicked itself back onto the bearing rail and came through and hit the person in the head, creating a recordable injury. So we have to make sure that we know that just because you hit the e-stop or you stop the machine doesn't mean that all of the energy is bled off. We'll get into a little bit about how to identify that here in a minute, but these are just basically some visuals you can look at and some things to be cautious so when you're working on the machines. Here's where you can find different types of stored energy. You got mechanical, pneumatic, hydraulic, gravity, chemical, other. When we think stored energy, a lot of cases we're just thinking, hey, the electrical, the e-stop is pressed. But it's a lot more than that. So all of these are areas that you can look at. Some facilities may have all of these, some may only have one or two of them, or a combination of them. So just keep these in mind when you're looking at a machine and saying, well, I just have to worry about electrical, because the electrical stored energy is not the only one you need to look at. And sometimes the electrical stored energy will factor into all of these categories, and they do cross over to each other. One thing I did want to mention, there is some definitions that are helpful tips and hints on looking at this. I will be sending out a copy of this presentation so that you can go back through this again and maybe use it to train internally, hang up your own signs, build your own programs, things of that nature. So what is controlled reliability for functional safety? So controlled reliability really gets into redundancy. Redundancy is key. You want to make sure that you've got multiple signals that are speaking to each other instead of just one signal making a decision. I use this on safety monitoring. I think it's relevant here too. Is the redundancy is you've got two runners in a relay race. One finishes across the finish line before the other one. You start asking as a coach, why did both of them not cross the finish line at the same time? There's got to be a problem. There's got to be a reason. You do the same thing with this. Is if you get a signal from a device of some sort and you don't get both signals at the same time, what's the reason? Did you get a break or a short in one? Did someone try to bypass it? What is that reason for that? There's a reason. And to get that, you have to have redundant devices in your system. So control reliability is really talking about the redundancy that you get. So be careful not to just grab any part and say, well, I'm going to change this valve or I'm going to change this drive, because it does matter if the redundancy isn't built in. So here's a handful of devices, the safety valves, servos, VFDs, through drive motors. These are all devices that you have to be careful of when you're choosing the right ones, because there are non-safety rated versions, which are not going to give you the redundancy and the feedback that you need to make sure that you've got a safe system, that it's continuously working. That you can get valves that aren't redundant and it could fail, and then your whole system is failing or off or provides a hazardous condition. The way you can to evaluate this is to do risk assessments, which again, we're going to get into that here shortly. But you want to make sure that you are doing your homework, or a professional is doing their homework to make sure that you've got the right products in your control panels. Here's a quick overview of a risk assessment. It's a critical part of functional safety, giving you basically a holistic view of your system. There's a handful of standards to use as guidelines or required to follow. A lot to sort through, a lot of math to do. Um, there's a whole process that it's not just walk up to it. Oh, this one product is okay. That one isn't okay, but because this one I'm okay. So you have to make sure that you are following the risk assessment process when you're developing your control reliability control system. And this is part of a system that you use. There's different types of software you can use. Um, Standards that will help you. It's sometimes hard to read the standards because sometimes whether they talk in circles, maybe they point to different regulations and bring you back. Sometimes it can be hard to follow. We just need to make sure that we are asking, why is it this way? How do we get to point A to point B? If we have to go out to point F, but bring us back to point B, these standards will help us get to that point. But again, that all happens through a risk assessment process. And then your desired outcome is basically once you're done with the risk assessment, you look at this and it will tell you where is your performance level, how is your machine acting, how is it going to perform, how is it going to act, and then you compare that against your goals. If you want a PLC, then your PLC, if it comes back with a PLD, you're great. If you want a PLD and it comes back a PLB, you've got some work to do. So there's tools out there to help you get this. But again, it all starts with a risk assessment because guessing, assumptions, um, looking at components individually can create a lower performance level of your machine. This here just gives you a quick overview of a simple circuit showing dual channel infrastructure. So you've got your machine power on, off, and you're going through safety relays. You've got your redundancy, and then you got your channel A's and B, your A and B. Dual channel control reliability detects single faults and safely removes power. So this just kind of just sums up a little bit about what we just talked about making sure that it's not just one straight signal, because if there is an issue in the line, say you're using a limit switch instead of a safety rated switch, and your contacts weld over, there's no monitoring devices in your control system to tell it there is a problem and could create a hazard. So this is just a simple layout for you to visualize what we're going through. This is usually found in the risk assessment process that is done. Sometimes companies have controls engineers on site that can do this, or hiring a TUV certified engineer to work through this process, looking at the architecture, your controls, and determining where you guys are at. Basically, everything is creating a baseline of where you're at, and then that will allow you to create a recipe of where you need to go and what that's going to take to get there. So we talk in categories, we talk in performance levels. This here is a quick overview of a circuit that could be wired category 3, category 4, the same from a schematics reference, dual channel within device monitoring. The difference is how you wire it with diagnostics, how you're checking it. So it's not just in the devices, it's also how you're wiring it, how you're using the devices. So we wanted to put up a quick diagram of here's what your system looks like, here's what it could look like, just with some simple changes. So the wiring is also critical. We've talked a lot about making sure you have the right devices. You have to make sure that you've got the right wiring in there that is going from device to device to device properly. So this is just an example here showing you that. Then this here would be a category 2 showing you just a single channel. So in this situation, this would not give you that well, let's call it peace of mind when you're on a machine. And with that peace of mind, this is all invisible to the operator. The operator is assuming that this machine is performing to this level. They're not assuming that it's performing to this level. So we have to be careful that the operator understands what they need to do with their machine, and we need to make sure that we give them what they need to make sure that the machine is acting properly. So, because they're not going to know that, well, I don't know what to watch for. I can get in here because the system will stop what to watch for on if I see a frayed wire, whatever that may be. We need to make sure that we are doing our jobs on the control side of making sure that we're giving you the right category levels for the systems that you have, so that the operators stay safe and your machine runs consistently and reliable. The factors that do play into controlled reliable systems are going to be devices such as safety switches, laser scanners, light curtains, safety radars, safety mats. They all have different category levels, different levels of protection. Safety switches could be a blade style, could be mechanical, non-contact, monitoring with RFIDs, electronic scanners, higher category level than a safety mat. Safety mat isn't as reliable as a laser scanner. So your devices are part of this evaluation, because you could have the best output device, but your input devices aren't correct, which is going to cause a failure on the front end and just tell the machine to run properly on the back end. So you have to make sure that you're using the right devices on the front end as well. And then you need to monitor those devices to get that redundancy. Are the two signals from the safety switch or the scanner, am I getting two signals simultaneously? The answer is yes. It's going to allow the machine to keep doing what it's supposed to be doing. If the answer is no, it's going to stop the machine, pause the machine, whatever that sequence is, and say, there's a problem. So input devices, monitoring those input devices, safety relays, safety controllers, safety PLCs, not PLCs, safety PLCs, and then your output devices, motors, contactors, safety valves, servos, VFDs. All of these all make up what a solid functional safety system should be working with, and these all work in conjunction, all hand in hand. So you have to make sure that you're doing your homework on all three to give you a proper system. It's not just, well, this device is a category 4, or this has redundancy, this is safety rated, this one's not, but I'm okay because I have this. They all go hand in hand. So you need to make sure that holistically you have a good system in place. Evaluating, hopefully part numbers are present. So you can check the certifications, you can grab those part numbers, look them up online, maybe you have them on your files, matching the device specs. You can ensure the capabilities and compatibilities across the board, prioritize the diagnostics, look for what happens, what does this device do if it does fail? Does it stop the whole machine? Does it pause the machine? Does it trigger the emergency stop? Does it stop right away? Does it ramp down? All of those, hopefully you have part numbers on your system with whether it's a model number, serial number, names, whatever that is, that makes it a lot easier to do these assessments. Challenges are taken on a case-by-case basis if that information is not there, which could default to, I don't know what this is, so we're going to caution on the safe side and we're just going to replace it. Because if there's no information, maybe it's just too old and should be replaced anyways. And then that will give you, along with the rest of your risk assessment, will then give you an idea of what do I need to do to replace this system? Do I need to upgrade it? Do I need to replace the whole system? Do I just need to replace components? Do I need to rewire this? Does the system lack redundancy or fault detection? Do I know when something's going to happen? Safety integrity can't be validated. that's it, you didn't do a risk assessment, or I don't know what this part is, so we're going to replace it. The hazardous motion can't be stopped because the drive motor ramps down. Whatever that may be, that gives you your roadmap of, okay, we did all of our homework. Here's what we have. Here's what we're dealing with. And now what we're going to do is we're going to create the roadmap of these 3 devices are fine. Those 4 devices need to be changed. We need to rewire this. We need to relay out the schematics, and let's put a plan together to get to your control reliability. Controls and automation engineers are typically the responsible party for upgrading control systems and output devices. They basically, once they have the risk assessment in hand, you have the meeting with your safety engineer that did the risk assessment. You discuss where the issues are and what we need to do to upgrade, give them the tips and tricks and ideas and direction and roadmap, and then they're responsible for upgrading these systems, swapping out parts on the machine, swapping out parts in the panel, rewiring. That is typically a responsibility of a controls or automation engineer to make those changes. And then here's just some examples of what some of these areas that they're going to pop panel open. They're going to see, okay, here's the contactors. We've got PLCs, or safety PLCs, controllers, all of that's drive motors. Here's the fluid power system. We need to make sure that we're not forgetting about our fluid power and our hydraulic systems. We need to make sure that all of that is all taken into consideration. So this is just an example of showing you what those engineers are going to be faced with once the evaluation and documentation has been done. Once the system is built, then some things to do for testing to make sure that is this going to fault, is it not going to fault? You want to tug on wires, you want to short your contactors, manually activate safety devices, basically do IO checkouts, making sure that is the light coming on when it's supposed to, is it not, is it giving me a fault? How am I checking this with cycling power on and off? How does it ramp up? How does it ramp down? So you want to be going through and testing everything and just not make the assumption. It's basically a trust but verify. You want to make sure that, okay, I know I did my job. I had good information from my TV certified risk assessment. I built the system. I've been doing this a long time. I know this is right, but verify it. We all get distracted. We all get busy. Maybe there's a faulty part that came in from the supplier. Maybe a wire came out from somewhere. Whatever that may be. Maybe you left for lunch and came back and you forgot where you left off and you missed tightening down a contactor. You want to make sure that you're validating that. You want to do a troubleshoot verification on the front end, making sure that this is ready to go into production. And then your schematics and panel layouts then can be finalized so that if you have to do troubleshooting in the future, or you need to show that this is now a reliable system, here is what this looks like. Here's what my panel looks like. Here's what my schematics look like. And then you put these hopefully digitally that you can save on your system, maybe print a copy, put them in your box for maintenance to look through if there is an issue. But updating these are a critical step in making sure that you can keep up with your reliable system. And then when you troubleshoot it, making sure that you're not putting inferior parts in if you have to change something out, or you put the wires back where they belong. If a wire does come out, wire burns up, whatever the case that may be. And then this kind of gives you a quick checklist that is easy to use, to follow. I'm going to open up the panel and I'm going to inspect it. Is it ready? Are all the wires labeled, terminated and secured? Are the schematics, are they matching the panel layouts? Are the fault simulations documented? If you did have any faults along the way, You want to make sure you document that, because if you do some upgrades, if you do some troubleshooting, you probably want to look back at those notes and say, you know what, when I first turned the machine on, this happened. So this is a normal condition, or we've made an exception for this condition. Those notes keep in your documentation. Any certifications that are available, are those in the file? Are you doing UL certifications? You need CE stamps. Are you just looking for the performance level that it's up to par? Are those available? Are those on the system? Terminal strips, are they neat, grounded, isolated where needed? No exposed contact conductors or loose components. Kind of just touch them, wiggle them around, make sure they're moving. Create to create maybe sparks inside because it's arcing, creating a potential fire. And then final inspection signed by the technician and engineer, making sure that that system was built the way it was supposed to be built based on your risk assessment. And then this just gives you, from all the information we just went through, kind of gives you a quick summary of how you handle control reliability, how you look at it, what you need to do. First one is understanding your system through education. You're going to do your risk assessment. You're going to look at your part numbers. You're going to evaluate your wiring. What am I dealing with? Where am I going to begin? And then once you've done the high level of that overview, what are the standards? What are my performance levels supposed to be? What is my standard? What is my goal that I'm trying to get to? Then dig into it with your risk assessment, going through and punching all those numbers into some type of software that will then give you an authenticated number that say, based on where you're at, this is what we're trying to deal with. This is what we need to get to. Here is our roadmap that we need to create and why. And then you start designing and redesigning your control system, schematics, panel layouts, start laying out what parts you need, getting all your documentation in order. And then you start building or rebuilding your control system. Once that system is built or rebuilt, then you take that information that you put together, start doing your testing. Do I have my documentation? Are my schematics updated? Are my wires solid? Are they labeled? Are my devices sitting in the box tight? Does everything look good? Any contaminants I need to take care of? Then you start, you finish that testing process, and then you close the loop through the validation and documentation. You fire up the machine and everybody signs off on it. You put it in the file and you've got your system that you want to trust, give that peace of mind to your operators that, hey, we've got a solid system here, but we're going to put everything in the system and then we're going to check it from time to time. Or if something fails, raise your hand, let me know so I can go back to the folder, get all my information out and do all my troubleshooting. And that brings us to the end of the initial training for the control reliability portion of our machine safety. You can read up more at PowerSafeAutomation.com. You can contact us via phone, forms on our website. You can email us. When I send out the information, you'll have my email address. And then if there's any questions about TUV certifications for the needs for the risk assessment, or to have us look at doing risk assessments for you, then I can bring my specialists in for that as well. So at this point, I am going to open this up for any particular questions and see what we might be able to help you out with. Anybody have any questions at this time? And if a question comes up after this, like I said, I'll get my email out. Some of you have my email address. A lot of you could have my email address from the invites. If you signed up through social media or found it on just on our website, let us know what those questions are, and we can answer that on a sidebar. And we have a question. Yes, Mary? Mary, do you have a question? I'm trying to unmute you on this side. Mary, if you'd like,
I think I got it.
There you go.
I was trying in the wrong spot. Excuse me. So thank you very much. I was trying to type it in the chat, but I thought it'd be easier for me to ask. And just from a layman, you did a great job explaining that. Thank you very much, Sean. And my question is just to get more of a visual for myself and maybe others is, can you walk through a scenario that shows what happens? So you have your input device, right? Your interlock or light curtain, let's say. And then once you put these monitoring and output devices on there for control reliability, can you give a scenario of what happens once those things are triggered? You know, so let's say you have an interlock on a machine, you open the door, the machine stops. If there's no control reliability, right, we're depending upon that. So when you put these the monitoring and output devices on there, what occurs at that point?
If you have a safety interlock that maybe have that higher category level, but your output device is not a safe state type condition, you open the door, it's going to tell the signal, hey, drive motor stop, conveyor stop, valve lock the air, whatever that may be. There may be some communication in there that it gets lost because it doesn't have the redundancy in it. And that drive motor could kick back on, or it could turn the conveyor back on. So that the redundancy of the communication all the way across the board could create unsafe starts or unsafe stops if you don't have that throughout the system.
Got it. Thank you very much.
You're welcome. Any other questions at this time? Okay, I appreciate everybody signing up and joining the webinar today. I will go ahead in the next day or two. I will be getting this out to you guys. There'll be a recording of this. I'll send the PDF of the presentation that we just went through, and you'll have my contact information. And then if there's any questions beyond that, you need on-site support, you need to jump on a Teams meeting to discuss that with myself or Marcus, we can certainly schedule that for you. And then maybe we get you on the other webinars. There's one coming up in December and then 3 more in January. So I appreciate everybody's time. Hopefully everybody has a safe day. Thanks, guys. Bye.